All right, so we're defining a subspace right now. And what a subspace is just a subset of a vector space that is also a vector space itself. So if you have some subset W of some vector space, we call it a subspace if you consider the same binary operation and the same scalar multiplication as your parent vector space, that W is also a vector space. It's a very natural definition. So when this does happen, we call W a subspace, and we usually use the less than or equal to sign for subspace, where we use the kind of the open, the little C, the curved C for a subset. So can anyone think of like a subspace? Like let's give well, okay, so first of all, you tell me, think about what you know about the axioms of the vector space, and how do you think we can figure out if a subset is also a vector space? So the big thing to realize is that we're using the same binary operations and the same scalar multiplication of the vector space. So think about the axioms. What axioms are given? So given this this fact that we're using the same binary operation and the same scalar multiplication, what are some given axioms? Axioms that we don't need to check. Think about the axioms of the vector space. Good. Associativity. And why not? Because if your binary operation is associative in V, of course it would be associative in a subset. Right? It's not a different binary operation just because it's on a smaller set. What else would be given to you? Commutative as well, right? And again, we're not changing the operation. So why would we need to check these, right? All right, what else do you think? Question, how about for the binary axioms? Is there anything else that would be given to us? So what are the binary axioms first? There's closed, commutative associative, and identity inverse. So we're saying that commutativity and associativity are given to us because we're using the same operation. Is anything else given to us when looking at subsets? No, yes, that's important, right? Just because the operation is closed in V, why should it be closed in a subset, right? If I have a vector space and some smaller set, it could be that you have two elements here and maybe they add up to outside the small set, right? That's perfectly, valid. We can think of examples later. We'll think of examples when that does happen. How about identity and inverse? Would those be given to us in a subset? Remember, subset is general. It's any subset. What do you think? Yes, meaning they're given to us, or yes, they're not given to us? Well, here's why they maybe wouldn't be given. Let's say, for example, let's say 0 is the identity element. V minus 0 is a subset. So there I gave you a subset that does not have the identity, right? If I have any subset without identity, then that's not given to us. Now, I do agree, if the subset did have the identity element, then it would be given, right? It would be the same 0. So, but the identity may not even be in the subset. So in that regard, it's not given. So does that make sense? Like if 0 is in the set, then great. We don't need to check that. But if 0 is not in the set, then it's immediately not a subspace. So it's not necessarily true the identity would be in the set. And how about inverses? Same thing, right? You could just form it so that inverses would not be in the set, and then you're done. So when checking for subspaces, already we would need to find or verify these 3 things. We would need to verify closure, identity, and inverse. Now, we'll think about later how we can reduce that even further, but for now, let's keep that. All right, so now let's look at the scalar multiplication axioms. All right, so what axioms are we given with scalar multiplication? So remember, we're using the same scalar multiplication as we are given in the vector space. Good, yeah, so if multiplication is distributive in V, it's distributive in W, correct. If 1 times V is equal to V in V, then 1 times W is equal to W in W, right? Because W is a part of V, so of course it should work out in W as well. And the last one, scalar, yeah, what's the last one? Can you remind me? What's that called? So we got the distributivity, the identity of multiplication. What was that last one? If you forget the exact word, remember, like, good, it's compatible. If you forget the word compatible, I would understand it if you said associative. Yeah. And of course, it's the same scalar multiplication, so it should also be compatible. So which axiom is not accounted for scalar multiplication? So remember, it's kind of like an axiom quote. So our 0th axiom that we talked about. What was the 0th axiom for scalar multiplication? Closed, yeah. So we don't necessarily know if it's closed. So, and again, if I have a vector in W and maybe I multiply it by a number, maybe it jumps outside, right? I know it can't jump outside of V, but it's not necessarily guaranteed it can jump outside W. All right, so we've boiled it down to only 4 things, right? Need to check closed under addition, under multiplication, and has identity, and has inverse. Okay, so my claim is this axiom here guarantees these axioms. Can someone tell me why? If I know that my subset is closed under scalar multiplication, how do you know that the identity exists, and how do you know that inverses exist? So think about that. If, let's say, X is in W, and W is closed under scalar multiplication, Y is 0 in W. And Y is negative X in W. So think about scalar multiplication. What number do you multiply to X to get 0, and what do you multiply to get negative X? Correct, yeah. If it's closed under addition, 0x is equal to 0. If it's closed under multiplication, negative 1 times x equal to negative x is in W, right? So what have we just done? So W, a subset of V, is a subspace of V if W is closed under addition and closed under scalar multiplication. Sure. Yeah, so the 0 and the 1, these come from your field. So the 0 is coming from your field is R, right? So scalar multiplication are things in R, real numbers. And if it's not real numbers, it's some other field that has analogous things to 0 and negative 1. Does that make sense? So the scalar multiplication is the 0. So maybe let's say this. Yeah, this 0 is a number. And this 0 is a vector. Does that make sense? Yeah, the negative 1 is coming from the field that's used in scalar multiplication. So for identity inverse, yeah. So again, this negative 1 is a number, and this negative x is a field. We didn't, sorry, is a vector. Yeah, fields. We're really going to only use real numbers. But all a field is that it has inverses, both additive and multiplicative, except for 0 for multiplicative. It has I wouldn't worry too much about the axioms for field. It's commutative, distributive, associative. So it's all the nice things. So real numbers are an example of a field. They have all the nice things that binary operations can have. Addition, multiplication, division, that would be existence of inverses. The negative 1 is defined as additive inverse to 1. So 1 like the number, it's not a vector. So again, don't worry too much about field, just think of them as real numbers. Okay, is that better? Remember, these are numbers. And they multiply vectors to get a vector, right? So 0 times x is the number 0 times the vector x, and that equals 0. That is a proof. I skipped over the proof because it's kind of clear. And we could do that proof. I think for homework you might have a proof like that. Yeah. If I wanted to be precise, if I want to put 0 the vector, sometimes I'll put a little arrow on top of the 0, and that will so we're not confused. So if you remember, like when we first kind of talked about vector spaces, sometimes when you talk about field elements, you may want to put like a subscript F for field element to distinguish it from the vector, or like 1F. That's the notation we used to say this is a field element. And as opposed to, I put a little arrow on top of the 0, I'm talking about the identity element in the vector space. Is that better? So when I have 0 just alone, I'm assuming that's a vector because I'm never going to be talking about a number alone when I'm talking about a vector space. When I have a number next to a vector, the number is always going to be called the scalar because I can never multiply vectors together. So, because that's not a thing in a vector space. Okay, so we found out that subspaces boil down to just closure under addition and closure under scalar multiplication. That's very nice. We've boiled down those 8 axioms or 10 axioms and boiled it down to our 0th axioms, right? So we don't really have 8 axioms to check. We just have these 2 0th axioms. So let's do some examples. So first of all, any subset that does not contain 0 is not a subspace. Is not a subspace. Right? If it doesn't contain 0, then it can't be a subspace because then it wouldn't be a vector space. So one thing I like to do when checking for subspaces is I go right to 0. 0 is the only element that needs to be in every subspace. So speaking of that, what do you think is the easiest subspace? So if V is a vector space, what is one subspace that you know? It's a random vector space. I'm not giving you a specific one. There are 2 subspaces that you know are subspaces. What's int? What's int? Yeah, 0 is a subspace. Oh, not empty set, right? Empty set. We proved that empty set was not a vector space, but 0 is a subspace. Let's check that. Is that closed under addition? Yeah, 0 plus 0 is 0. Good. That's all I have to check. Is it closed under multiplication? Yes. Alpha times 0 is equal to 0. Good. Done. What's the other subspace? So remember, not 1, right? 1, well, this is a vector space, right? Remember, we can't have 1 and -1 because those are like numbers, right? One thing about vectors. So we don't know if these are matrices, right? We don't know what these are. We know 0, it does exist. Correct. V itself. V is a subspace of itself. This one's kind of the boring one, right? So 0 is a subspace of V, and V is a subspace of V. Right, subsets could include the whole thing, right? We define that. If it's not, right, obvious is always tricky. It's based on kind of the definitions, right? And if it's not, if W is a subset of V and W is not equal to V, then W is called a proper subspace. So this should mirror our definition of proper subset. proper subset was the one that was not the whole space. And 0 is called the trivial subspace. It's trivial. It's the most boring one. And if W is not equal to 0, W is called non-trivial. So non-trivial subspaces, non-trivial proper subspaces are the ones that are not 0 and the ones that are not V. So when I say this trivial subspace, I'll be talking about 0. Okay, so let's do some like actual examples. All right, so let's look at the plane. So we talked about vector spaces on the plane last time. So let's think about what would, I said subsets, I meant subspaces. Okay, can someone say, is the x-axis a subspace? So first of all, how do you describe points on the x-axis? It is going to be true, yes. So let's say why that's true. What are points on the x-axis? Good. The x-axis is all points that are 0, other way around. A comma 0, right? Or A comma 0. So let's first check if it's closed under addition. How would you check if it's closed under addition? So if all points on the x-axis are A comma 0, so this could be like 1, 0. This would be like -1, 0, -2, 0. How would you check if it's closed under addition? What would you need to do? All right, so what does closed under addition mean? Good, add A 0 plus B 0. So we want to check if A 0 plus B 0 is in the set. And yes, it is. A plus B comma 0. And why is it in the set? Because it is of the form number comma 0. So that's good. That's the definition of something on the x-axis, right? If it's number comma 0. Because now we need to check if it's closed under scalar multiplication. Is that true? So how would you check if it's under scalar multiplication? What would I need to check? Yeah, so instead of x, I might say alpha. Is alpha A 0 in the set? And it is, right? Because you know how to multiply that. It's alpha A times 0, and that is in the set. Right, because it's of the form number comma 0. It was a subspace. Then we're done. Yeah, I don't have to check anything else. That's what makes those subsets nice. Subspaces nice. Right, I only have to check 2 things: closure under addition and closure under scalar multiplication. So we're done. All right. Do you think the y-axis is? Yes. And if you don't see that, just try doing it. Right. Notice that whenever you add, you always get a number in the second position, and you always get a 0 in the first position. That's what definition of the y-axis is. If you multiply by a number, You'll always get a 0 in the first position, and you'll always get a number in the second position. Okay, so let's do another one. Let's do the line y equals x. Is this a subspace? All right, can you tell me how to describe points on the line y equals x? This is a very important part. Describe the points. Like, what are the rules for things to be in your set? Correct, x equals y. So you could say x comma x, or a comma a, whatever letter you like. So it's all points where the first and second coordinates are the same. Is this a subspace? So what is the first thing you need to check? Closure. So how would you do addition, closure under addition? Good. Yeah, so however you like to do it, you can say xx plus aa, sure. What is that equal to? It's x plus a, x plus a. Can you say why is that in the set? Why is it in the set? Good. It's of the form number, number. Let's say same number, same number. Right, x and y are the same, good. And let's do scalar multiplication. So I have alpha times xx, and that's equal to alpha x, alpha x. Same. All right, so does that make sense? Yes. Okay, let's do another one. Y equals x plus 1. Is that a subspace? I doubt it, yeah. Well, why not? My hint is you do not have to actually do anything. There's something we said earlier on. Yeah, what's wrong with a plus 1? What's not in your space that should be? What's not in your set that should be? 0, 0, right? There's no identity element. So not a subspace. Right? So sometimes you don't need to do anything, right? I think the identity element is the easiest thing that should be in every space, every vector space. So if you can see one that doesn't have 0, 0, then all bets are off, just done. All right, let's do another one. Let's do y equals x squared. Is that in your space? Is that a subspace? Okay, well, we want to check. How would you check if it's a subspace? It does have 0, 0, but what else do you need to check for it to be a subspace? So how do you define points on y? It's not a subspace, yeah. How do you define points on y equals x squared? Well, the y is x squared, right? X squared. So what do you have to do? You have to give me a pair of points, right? So let's do x squared plus y squared, a squared, yeah. What is the sum? It's x plus y and x squared plus y squared. So now can you tell me why it's not a subspace? What would this need to be for it to be a subspace? For it to be in the set? Well, not quite the same number, right? But what should it be? Right, it should be the square of x plus y. Should be x plus y quantity squared. Right. Because that would be closure, right? This is the definition of the set. Right, it's always number and number squared, right? But right here we don't have number squared, right? We have number plus number, then number squared plus number squared. Yeah. So this is checking if a sum of elements is in the set, right? That's the closure of addition. Yeah, there's another, yeah, there's definitely, just by looking at it, you can tell why it wouldn't be. Here's one way you can look at it. What do we know about addition of vectors in the plane? Let's take this vector, which is in that set, and let's take this vector, which is in the set. Where is the sum of those vectors? How do you find the sum of those vectors? Well, yeah, so it doesn't have to be the y-axis, but it's somewhere interior, right? So, right, you take this quadrilateral, right? And then you draw your diagonal. And yeah, you'll never get on the curve. Does that make sense? You can always find a pair of vectors that sum outside. So what do you think would be a guaranteed, knowing that, how do you know what all subspaces look like? What do all subspaces need to look like? Yeah, that alone tells you all subspaces need to be aligned. And what's special about the line? What's special about the line? It needs to go through the origin. Yeah. All subspaces of R2 are lines to the origin. Can you think of another subspace other than lines to the origin? So remember, early on we talked about those easy subspaces. Yeah, you can just have the origin. Or maybe we'll describe it like this, however we like it. And what else could it be? So what do you mean the same? So remember, R2 is the whole plane, right? It's like everything. So everything in this case is R2. Remember, R2 is all 2x2 vectors, or the plane. All right. So any questions on that? So we've just described all subspaces of R2. They must be lines to the origin. Right? Otherwise, we can find a sum that goes outside. Right? If there's ever a line that you can make that's not parallel, right? You can always find a sum that goes outside. All right. Let's do some more. Oh, question. And I think the answer from before will give to you. If W is a subset of V, subspace of V, And let's say U is a subspace of V. Is W union U a subspace of V? What do you think? Okay, we have a yes and we have a no. So why do we think a yes or why do we think a no? So let's first of all, let's maybe do an example. Give me a subspace of V. Where let's say V is R2. Give me a nice subspace. What's the subspace that we talked about in R2? So remember, what do subspaces need to be? Sure, X equals Y. Give me another subspace in R2. Sure, Y equals 0. So that's the x-axis. What is our union? Describe to me what the union is. Let's remember what union is. What's the union? So by both of them, it just means both sets combined. Yes, it's just this X shape, right? Is that a subspace? No, yeah, not a subspace. It's not even equal to itself, right? That's a different thing, which you'll think about in the homework. That's the sum of the two spaces. But the union, sure, let's explain why. The union is literally just these vectors and these vectors. That's all union is, right? There's no other vectors in the set. So it's literally x or x0. So let's give a pair of vectors that sum outside. Let's take this vector here, and let's take this vector here. What is the sum of those two vectors? Where would that go? Yeah. So what do you mean by point is a vector on one line and a vector on the other line, right? What is the sum of these two vectors? It's like somewhere out here, right? That's the idea. Union is literally just take these vectors and let's take these vectors, right? I'm not doing anything to the vectors, I'm not adding them. I'm just looking them together. Right. So the union is just literally, I'm looking at them both as one set. That is true. If I only added W things and I only added U things together, then it would be fine. But here I'm allowing both of these things to be in the space or in the set. Yeah. So addition of a subspace is a little bit different. So you'll prove this in your homework. An addition of subspaces is all forms W plus V where W is in W and V is in V. So that's a very different thing. But that's a homework problem. I'll let you do that. But actually, this is a homework problem too. So union just means I'm looking at both of them. Enclosure under addition still means if I take any two elements in the set, right, and W is in the set, things in W are in the set, and things in U are in the set. So when I talk about my binary operator, I still want to consider things in W and in U. So the answer to this is not necessarily. Can you give me an example when the union is a subspace? Good. When one of the things is 0, what would another example be? So what about 0 in relation to W makes that true? Why is union with 0 fine? It's not moving outside. Yeah, so because it's inside. Yeah. So in general, what can you say? If U is a subset of W, then W union U is a subspace. Because you're not going anywhere. Or when W union U is equal to W or something. So yep, that's an example. All right, so let's do some more. Okay, so last time we did talk about the 2x2 matrix or any n by n matrices forms a vector space with matrix addition and scalar multiplication. All right, so let's think about subspaces of 2x2 matrices. Okay, can you tell me if this is true? Diagonal 2x2s? Do those matrices form a subspace of 2x2 matrices? So what would you need to check? What are diagonal 2x2 matrices? Can you describe what those are? What does diagonal mean again? Good, yeah. So it would be anything of the form x, 0, 0, y. All right, so we want to check closure, right? So let's do x, 0, 0, y plus a, b, c, not that, right? That's not a, 0, 0, b. Is this sum diagonal? Yes. X plus a, 0, 0, y plus b. So good. So let's take alpha times x, 0, 0, y. Is that scalar multiplication diagonal? Yes. Good. Done. So diagonal 2x2 matrices form a subspace of 2x2s. Let's do another one. Let's do symmetric. Does that form a subspace? So first of all, define symmetric 2x2s. What would the matrix look like? So what does symmetric mean again? Good, yeah, so it's like A, B, B, C. All right, so now let's check for closure. All right, so as I'm writing it, you tell me if this is, the sum will be symmetric. What do you think? Is this symmetric? Good. And why is it symmetric? What tells you it's symmetric? Yeah. So these elements need to be the same. Good. Now let's check for a product. Well, is this symmetric? Good. So these are the same, so good, it's symmetric. All right, so kind of getting the idea of what subspace is. It's really easy to check, right? I mean, if easiness depends on, how the binary operation works and how your set looks, but you only have two things to check. Okay, let's think about polynomials. So polynomials is a big space, right? I can have polynomial of degree 10, a polynomial of degree 100 million, right? But what do you think subspaces would look like of polynomials? Let me ask you this. Is the set of nth degree polynomials, let's even be more specific, let's 7th degree polynomials, does that form a subspace? Seventh, yeah, so why do you think? So remember, what's the easiest check? Does it have a zero? Does it have a zero? Yeah, does it have the origin? What is the origin? What is the identity for polynomials? What is the identity polynomial? Zero. Yeah, identity polynomial is zero. Is zero a 7th degree polynomial? No. So it's not a subspace. However, how can we make it a subspace? So everything else is fine, right? Adding two 7th degree polynomials. What's a 7th degree? Where you have like a x to the 7th plus blah, 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 right? B x to the 6th plus c x to the 5th, something x to the 4th, something x to the 3rd, something x squared. Well, that was supposed to be an x squared. Yeah, where 7 is the highest degree. So yeah, so if we amend this and just say polynomials of degree less than or equal to 7, is that a subspace? So if we allow for lesser degree, would that be fine? Yes, it would be. And why is the only problem with the 7th degree polynomial is that it didn't have 0. So if I just say, well, actually here, let me give you an example of even why this is even also bad. Let's do x to the 7th plus x plus negative x to the 7th plus 2x. It would be subspace of polynomials, right? Because it's still closed under scalar multiplication and closed under, wait, 7th degree polynomials is not a subspace, right? Because it doesn't have, because a couple things happen. Like for example, here are two 7th degree polynomials. What do they add up to? They add up to something that's not 7th degree, right? It goes outside the space. More particularly, it doesn't have the 0 polynomial. But if we add this extra condition of just have my space be all polynomials of degree less than or equal to 7, but the idea is 7th degree polynomials is not a subspace. So it's not a subspace of I'm just making up because this is nth degree polynomials, and polynomials of degree less than or equal to n. There's a lot of subspaces. So all linears are subspaces with n constants. All, does that make sense? So like, here, let's define Pn equal to polynomials of degree less than or equal to 2n. So in particular, P0 is a subspace of P1, is a subspace of P2, is a subspace of P3, right? All of these are subspace of the thing we call polynomials. These are all constants. These are all constants and linear terms. Yeah, it's all seventh and lower. That's the idea. That's why it's degree less than or equal to n. Yes, instead of just seventh. It is including seventh, yeah? Or equal to. So if it was just less than, that would be sixth degree. That's fine. So yeah, so with polynomials, like, you can't just take the degree and let that be your subspace, right? You have to include everything before it. And the main reason is because you can do this thing where you can add two like seventh degree polynomials, for example, and get something that's not seventh degree. But the main thing is you cannot add two seventh degree polynomial. Again, 7 is not special. And get a polynomial of higher degree. You agree with that? That's essentially, that's the closure property. I can never go higher than degree 7, no matter how much I add. All right. So that's polynomials. Now, let's do some special things about matrices. Let's get back to matrix algebra a bit. Let's take the matrix equation AX equals B, where X is n by 1. Is the set of solutions a subspace? So X is an n by 1 vector. So I can think of it as an Rn. So vectors of length n. And I want to look at all the solutions to AX equals B. A is not necessarily n by n, it's just any matrix AX equals B. Does that form a subspace? Hey, you tell me. It is going to be no, so you tell me why. So give me two solutions for AX equals B. Just give me any two vectors. Let X, good. Yeah, the sum of two solutions don't have to be a solution. Let X and Y be solutions. So AX is equal to B and AY is equal to B. What would need to be true for this to be a subspace? What would I need to check? What would also need to be a solution? So what does closure mean? X does not have to equal Y, right? Oh, good. Yeah, 0. That's a bit even better. 0 is not in the set. Good. Yeah, that's immediate. And why? Because B is not necessarily 0. Good. So what if B was 0? Now 0 is in the set, right? Does this? Yes, this will be true. Does this form a subspace? So we need to prove it. Okay, what do I need to check if this is a subspace? So this is X is n by 1. What do we need to check? Closure, yeah. So let X be and Y be a solution. Okay. What does closure tell me? If X and Y are solutions, then what would also need to be a solution? What would need to be a solution? If X and Y, good. X is X plus Y a solution. So let's check that. So I have AX plus Y. What is that equal to? Well, give me the steps to get to 0. It is equal to 0, but what are the steps? Good, AX plus AY by the distributive property. And both of these are 0. So check. All right, what else do we need to show? What's the other thing? Closure of what? Yeah, so is alpha X a solution? A times alpha X. What can I do with that alpha? Do you remember how to work with scalars? I can move it outside, yeah. This is A alpha X. But alpha X, or AX, but AX is equal to 0. Cool. So this forms a subspace. The set of all X such that AX equals 0 is a subspace of Rn, where X is n by 1. Can you tell me if A is n by n and non-singular, what is the set? You know exactly what the set should be. A is n by n and non-singular. What is the set of all solutions to X equals 0? 0. Not empty, but 0. That's different. So that's something about non-singular matrices. This is always 0. So we're going to give a special name to this type of set. So we're going to call this the null space. So the null space of a matrix called NA is the set of solutions to the homogeneous system. Set of solutions to the homogeneous system. Now notice that I didn't say anything about n by n, except for non-singular. But this is actually for any matrix, for any dimension. It could be rectangle. So for example, if A is m by n, what vectors live in NA? What sorts of vectors live in NA? It's a dimension question. Do you remember? What dimension would X need to be? What type of vector can you multiply to A? Do you remember matrix multiplication? When can you multiply two matrices? N by n is n by something, yeah. So if they're vectors, it's n by 1, what we call vectors. So it's Rn. Yeah, n by n is these are matrices, right? N by n is row and column. Yeah, so so I won't do a specific example because we've done these all the time, but the null space of like 1, 2, 3, 4, 5, 6, 7, 8, 9, which I believe is non-singular, is just equal to the set of solutions that make the 0. And you know how to do that, right? You just set up a augmented matrix and solve. And that gives you your set. All right, so any questions about that? I'm not going to do an example because we've done these examples really. All right, let's do something that is interesting. All right, so let's think about what it means to be closed under addition and multiplication. Okay, so can someone say what does it mean to be closed under scalar multiplication? Let's just say that again. If x is in V, what must also be in V? Yeah, on the line. So if it's not just on the plane, so what's the kind of generalization of that on the line? Alpha x. Yeah, alpha x is in V. So this, and now we know for closure under addition, if x is in V and y is in V, then x plus y is in V. So can you say why this makes sense? Also, alpha x plus beta y is in V. Is that true? So this is in V, right? This is just V. Random vector space V. Is that okay? So the set is V, the vector space, whatever it is. It's an arbitrary thing. Does this statement make sense though? If I have a vector space V, does it make sense that alpha x plus beta y must be in V? Yes, no? Okay. Let's say this. Let V be a vector space. Let x and y be in V. Let's let alpha and beta be in R. Alpha x plus beta y is in V. Yes, because this is in V, right? Because this is scalar multiplication. Yeah, if I say it's a vector space, then it passes all axioms. Yeah. Yes, I'm just reciting. Yeah. So so I'm building up to another true thing about vector spaces, and which will be a definition of something else. So yeah, so alpha x is in V because it's closed under scalars, and beta y is in V because it's closed under scalars, right? But then their sum must be in V because it's closed under addition. What does this look like? This should look familiar to you, this kind of formation. So I'll give you another thing that's true. Good, yeah, this is just a linear combination. The worst. I'll get ready for some more. We'll get more practice with them. That's such a linear combination. So this is also true about vector spaces. Vector spaces are essentially closed under linear combinations. Does that make sense? If it's closed under addition and it's closed under multiplication, then of course it's closed under linear combinations. They're the same thing. So why is this so cool? The claim is that this is cool. That means that all linear combinations of sets are vector spaces, or subspaces at least. So let V be a vector space. Let V1, let's start easy, V2, be vectors. All linear the set of all linear combinations of V1 and V2 is a subspace of V. Does that make sense? So we essentially said that, so subspaces, all they are just addition and scalar multiplication. But that's just what linear combinations are. They're addition and multiplication. So essentially, if we know that fact, we can construct subspaces. So what are the set of all linear combinations? Well, here's a linear combination. It's alpha V1 plus beta V2. Can someone give me another linear combination? Sorry, we're out of time, but let's just use other Greek letters. Oh, those are good choices for a bad reason. Delta, V1, and Omicron, V2. Yeah. So let's add them up. You get alpha plus gamma V1 plus beta plus Omicron V2. Oh, I put gamma, I meant to put delta. But this is still a linear combination. Does that make sense? If I just take a set of vectors and look at linear combinations of them, that forms a subspace. So we'll define this thing as span. As the set of all linear combinations. So we'll talk more about that next time. And this forms a subspace of V. Whatever V is, we don't know what it is. Okay, so we'll do more of that next time. So I'll stop recording.